Tonight, I want you to look up. Not at the stars, not yet. Just imagine the sky as it was this morning. Blue, quiet, ordinary. The sun rose the way it always does. Warm light spilling through your window. Another day beginning beneath the same star that has watched over every moment of human history. Hello, and welcome to Infinite Science. We grow up with the sun. We take it for granted. It becomes part of the background of existence, reliable, distant, harmless. A bright disk we're told never to stare at. Something we learn about in school and then forget because it simply is. It's there when we wake up. It's there when we go to sleep. It arcs across the sky with such reliability that we've built our entire civilization around its rhythm. But here's what we don't think about. We have never truly seen the sun. Not as it actually exists, not up close, not as the thing it really is. Because if we could somehow stand at the edge of that star and witness what is happening there, we would see something that doesn't belong in the same sentence as the word calm. We would see storms made of fire and magnetism. Storms that tear across the surface at speeds that shatter comprehension. Storms so large they could swallow Jupiter whole. Storms that carry more energy than every nuclear weapon ever built, multiplied by billions. We would see a star at war with itself, and we would realize we've been living inside its weather all along. The sun is a star. We say that so casually, but let the weight of it settle. That object in the sky, the one we use to plan picnics and check the time, is the same type of thing as every point of light you see at night. It just happens to be close. 150 million kilometers away. Which sounds vast until you realize that in cosmic terms, the sun is practically touching us. It is the only reason anything exists here. Every plant, every breath, every thought you've ever had was powered by a reaction happening in the core of that star. Hydrogen fusing into helium, releasing energy, sending light across the void. 8 minutes and 20 seconds later, it reaches Earth. It warms the oceans. It splits water into oxygen. It drives photosynthesis. It makes life possible. And because it does this every single day without fail, we treat it as furniture. Think about it. You've seen the sun thousands of times. But have you ever truly seen it? Have you ever stopped and tried to hold in your mind what it actually is? Here's an analogy. Imagine you've spent your whole life next to a campfire. You know it gives off heat. You know it glows. You've roasted marshmallows over it, warmed your hands, told stories around it. The flames dance. The wood crackles. You understand fire because you've lived with it. It's comfortable, familiar, safe, as long as you keep your distance. Now imagine someone telling you that's not a campfire. That's a contained thermonuclear explosion held together by its own gravity, burning at 15 million degrees at the center, fusing the building blocks of matter itself, converting mass directly into energy according to Einstein's most famous equation. Every second, it destroys matter and turns it into pure radiation. You'd say, no, that's just a fire. But you'd be wrong. The sun is not a campfire. It is a nuclear furnace 109 times wider than Earth. You could line up 109 Earths across the sun's diameter, edge to edge. You could fit 1.3 million Earths inside its volume. Think about that. More than 1 million Earths could be packed inside the sun. And if you held a coin at arm's length toward the sun, that tiny disk, maybe 2 centimeters across, would be covering a region of space larger than a dozen Earths standing side by side. The sun contains 99.86% of all the mass in the solar system. Jupiter, Saturn, all the other planets, all the moons, all the asteroids, all the comets, all the dust. Everything else combined is just 0.14%. The Sun is not just the center of the solar system gravitationally, it is the solar system in terms of mass. Every empire that ever rose, every war ever fought, every word ever spoken, every song ever sung, it all happened under this star. We have never known a single moment without it. Ancient Egyptians worshipped it as Ra, the god who sailed across the sky in a solar bark, dying each night and being reborn each dawn. The Aztecs called it Tonatiuh and believed it needed blood sacrifice to continue its journey across the heavens. Greeks knew it as Helios, driving his golden chariot from horizon to horizon. The Inca revered it as Inti, the divine ancestor of their emperors. In Norse mythology, the sun was Sol, chased across the sky by a wolf named Skoll, who would one day catch and devour her during Ragnarok. In Hindu tradition, Surya rides a chariot pulled by 7 horses representing the 7 colors of light. In Japanese mythology, Amaterasu is the sun goddess, so important that when she hid in a cave, the world was plunged into darkness until the other gods lured her back out. Every human culture, everywhere on Earth, in every age, has looked up and tried to understand what that light means. They built monuments aligned to the solstices, Stonehenge, the pyramids, the temples of Angkor Wat. They tracked the sun's path to create calendars, to know when to plant and harvest. And despite all our history with it, despite our absolute dependence on it, despite thousands of years of observation, we have no idea what it's really doing. We see a smooth, glowing circle. We think we understand it. A ball of gas burning in space. Simple, predictable, but we've never experienced it up close. We've never felt the plasma currents tearing through its atmosphere at hundreds of kilometers per second. We've never stood at the edge of a sunspot and watched magnetic fields twist into chaos. From 150 million kilometers away, everything looks peaceful. But peace and distance are not the same thing. Consider this. If you could somehow fly toward the sun in a spacecraft at the speed of a commercial airliner, about 900 kilometers per hour, it would take you more than 19 years to reach it. 19 years of continuous flight just to cross that distance. And for almost all of that journey, the sun would look like a point of light, barely different from how it appears from Earth. Only in the final weeks would it begin to swell, to reveal itself as something vast and terrible. We think we understand the sun, but we have never actually seen what it is doing. Let's start with something simple. What does the surface of the sun look like? Your instinct is probably to imagine something solid, a burning shell, maybe molten like lava, but still a surface. A place you could point to and say, that's where the sun begins, a boundary between the star and space. But here's the problem. The sun has no surface. There is no boundary, no edge, no moment where the star starts. What we call the surface, the photosphere, is just the layer where the sun becomes opaque enough that light can finally escape. It's not a place, it's a depth, a threshold of density. The photosphere is where the optical depth equals 1, where a photon has about a 50-50 chance of escaping into space versus being absorbed again. Think of it like looking into fog. At some point, you can't see any deeper. That doesn't mean there's a wall there, it just means the fog is too thick. The sun is the same. The photosphere is where it becomes too opaque to see deeper. But there's no solid anything beneath it. If you could somehow survive and descend into the sun, you'd never encounter a surface. You'd just move through increasingly dense plasma, getting hotter and hotter until you reach the core. The photosphere is only about 500 kilometers thick, a thin shell around a star that's 1.4 million kilometers in diameter. That's like the skin on an apple, if the apple were the size of a star. And it's made of plasma. Not gas, plasma. The fourth state of matter, solid, liquid, gas. Plasma is what happens when you heat gas so much that electrons are ripped free from atoms. What remains is a soup of charged particles, nuclei and electrons swimming separately, no longer bound together. Plasma is the most common state of matter in the universe. More than 99% of the visible matter in the universe exists as plasma. Stars, nebulae, the interstellar medium. Solid matter, like the ground beneath your feet, is the exception, not the rule. The temperature at the photosphere is 5,500 degrees Celsius, hot enough to vaporize any known material in an instant. Iron boils at 2,862 degrees. Tungsten, with the highest melting point of any element, melts at 3,422 degrees. Nothing we could build could exist there as a solid. If you could zoom in, if you could see the photosphere in exquisite detail, you wouldn't see a smooth, glowing shell. You'd see it boiling, enormous convection cells, each one the size of Texas or France, rising and falling in a slow, churning rhythm. Hot plasma rising from below, cooling, darkening, sinking back down, over and over. This is called granulation, and it's happening across the entire visible surface of the sun, all the time, without pause. Each granule lasts about 8 to 20 minutes. They appear as bright patches, hot material rising from the interior at about 500 meters per second. They spread outward. As the plasma cools and releases energy, it darkens. Then it sinks back down along the edges, forming dark lanes between the bright centers. The pattern looks almost cellular, like a honeycomb made of fire. The scale is hard to grasp. A single granulation cell is typically about 1,000 kilometers across. That's roughly the distance from New York to Miami. Some larger ones can be 2,000 kilometers or more, and there are millions of them covering the sun's surface at any given moment. If you watched a time-lapse of the sun's surface over an hour, you'd see it seething, a living texture, never still, always moving. Bright cells appearing and fading, material flowing upward and downward in patterns that look almost organic. Imagine an ocean, but instead of water, it's hydrogen, and instead of waves, it's cells of superheated gas the size of countries, each one carrying the energy of millions of nuclear bombs, rising and collapsing in patterns that shift every few minutes. You are not looking at a ball of fire. You are looking at a process. Beneath the photosphere, there's the convection zone, a layer about 200,000 kilometers deep where energy is transported by bulk motion of plasma. Hot material rises, cool material sinks, creating massive circulation patterns. Below that is the radiative zone, where energy moves not by convection, but by radiation. Photons bouncing from particle to particle, slowly working their way outward. And at the very center is the core. The core is where the magic happens, where hydrogen becomes helium, where mass becomes energy, where the sun lives. The conditions there are beyond comprehension. The temperature is 15 million degrees Celsius. The pressure is more than 250 billion times Earth's atmospheric pressure at sea level. Hydrogen nuclei, protons, are packed so tightly and moving so fast that quantum tunneling becomes possible. They tunnel through the energy barrier that normally keeps them apart, fusing together. 4 hydrogen nuclei combine to form one helium nucleus. But here's the key. The helium weighs slightly less than the 4 hydrogen nuclei did, about 0.7% less. That missing mass doesn't just disappear, it becomes energy, E equals mc squared. Every second, the sun converts about 4 million tons of matter into pure energy. 4 million tons every second for 4.6 billion years. And it will continue for another 5 billion years. The total energy output of the sun, its luminosity, is about 3.8 times 10 to the power of 26 watts. That's 380 septillion watts. The sun produces more energy in 1 second than humanity has used in all of recorded history. A photon is born in that inferno. A gamma-ray photon carrying tremendous energy. It begins to move outward, but it doesn't travel in a straight line. The core is so dense that the photon collides with particles almost immediately. It's absorbed, re-emitted, scattered, over and over. Each collision changes its direction. The photon executes what physicists call a random walk, a drunkard's path, staggering in random directions, slowly drifting outward, but taking an incredibly inefficient route. It takes that photon tens of thousands of years to fight its way from the core to the surface. Some estimates say 50,000 years. Some say 100,000. Some say as much as 1 million years. And as it travels, the photon loses energy. It started as a high-energy gamma ray. Through countless interactions, it gradually transforms into X-rays, then ultraviolet, then visible light. By the time it reaches the photosphere, it's a relatively low-energy photon in the visible range, the yellow-orange light we call sunlight. And then, finally, it breaks free. It crosses the photosphere. It enters empty space. 8 minutes and 20 seconds later, it reaches Earth. It enters your eye. It triggers a chemical reaction in your retina. An electrical signal travels to your brain, and you see sunlight. The sunlight touching your skin right now began its journey before human civilization existed, before we built the pyramids, before we invented writing, before we learned to farm. That photon is older than recorded history. The sun is not a simple object. It is a theater of continuous transformation, a cascade of processes operating on timescales from milliseconds to millennia. We are not looking at an object. We are looking into a process. Now we go deeper, because the sun isn't just hot. It isn't just massive. It's something else, something harder to see, but far more dangerous. The sun is a magnetic machine. Here's why that matters. Plasma, the charged ionized material that makes up the sun, conducts electricity. And wherever electricity flows, magnetism follows. They're two sides of the same coin. Moving charges create magnetic fields. Changing magnetic fields induce electric currents. The sun is full of moving charges. Convection cells dragging plasma up and down. Rotations spinning plasma around the star's axis. Turbulence churning the interior. All of this motion generates magnetic fields through a process called the dynamo effect. The dynamo effect is how planets, stars, and galaxies generate their magnetic fields. Take a conducting fluid, plasma in the case of the sun. Set it in motion. The motion of charged particles creates electric current. That current generates a magnetic field. And if the motion has the right geometry, the magnetic field can enhance the motion, which strengthens the field further. It's a feedback loop, an engine that converts kinetic energy into magnetic energy. Not small fields, not neat, simple dipoles like a bar magnet. Massive, tangled, chaotic magnetic fields that stretch from deep in the interior all the way out to the corona and beyond, reaching into interplanetary space, influencing the entire solar system. The strength varies dramatically. In quiet regions, the field might be only a few Gauss, comparable to a refrigerator magnet. But in sunspots, the field can reach 3,000 to 4,000 Gauss, thousands of times stronger than Earth's magnetic field. In the most intense cores of large sunspots, field strengths can exceed 6,000 Gauss, strong enough to affect the quantum states of atoms, to split spectral lines in a phenomenon called Zeeman splitting. Now, here's the key. The sun doesn't rotate like a solid object. It can't because it isn't solid. Different parts rotate at different speeds. This is called differential rotation. The equator spins faster than the poles. At the equator, the sun completes one rotation in about 25 days. At the poles, it takes closer to 35 days. That's a difference of 10 days, a 40% variation from equator to pole. Now imagine what this does to the magnetic field. Start with a simple north-south magnetic field. Now start rotating the sun. The equator pulls the field lines around faster than the poles. The field lines start to stretch. They wrap around the sun like thread being wound around a spool. After one rotation, they've wrapped once. After 10 rotations, 10 times. After many years, hundreds of times. The field lines get tighter, they get more twisted, they coil around each other. They form helical structures spiraling around the sun's interior like cables wound too tight. And here's the important part. Twisted magnetic field lines store energy. Just like twisting a rubber band stores elastic energy, twisting magnetic field lines stores magnetic energy. Imagine taking a rubber band and twisting it. Once, twice, 10 times. The band gets tighter. You can feel the tension building. It wants to untwist. It's storing potential energy. If you twist it enough, it kinks. It coils up on itself. And if you keep going, it snaps. That's what's happening inside the sun. Magnetic field lines get stretched, twisted, wrapped around the star hundreds of times over the course of years. The energy in a single twisted magnetic flux tube can be equivalent to millions or even billions of nuclear weapons. We're talking about energies on the order of 10 to the power of 32 ergs, more energy than humanity has ever produced in all of history. And eventually, that energy has to go somewhere. The twisted field lines become buoyant. Magnetic pressure inside the flux tube makes the plasma within less dense than its surroundings. Buoyancy takes over. The flux tube begins to rise, fighting its way through the convection zone towards the surface. It's like a bubble of air rising through water. The journey can take months or years. The flux tube has to fight against the downward flow of cool plasma in the convection zone. But gradually, driven by buoyancy, it rises. And when it finally breaks through the photosphere, it erupts into the corona. The field lines form loops, enormous arches of magnetism extending hundreds of thousands of kilometers into space, reaching out like the arches of an impossibly vast cathedral. Plasma becomes trapped along these field lines, following their curves like beads on a wire. The loops glow in ultraviolet and X-ray light. They're beautiful, delicate structures connecting points on the sun's surface, glowing against the darkness of space. But they're not stable. They're under tension. They're storing energy. And they're constantly shifting, evolving, interacting with other field lines. And where those field lines emerge from the surface, something visible happens. The surface changes. It darkens. It cools. Sunspots appear. A sunspot looks like a dark blemish on the sun, a shadow, a flaw in the otherwise perfect, uniform glow. But don't be fooled by the word dark. A sunspot is still about 3,800 to 4,000 degrees Celsius, hotter than molten lava, which is around 1,200 degrees, hotter than any blast furnace humans have ever built. It only looks dark because the surrounding photosphere is even brighter. about 5,500 degrees. Place a sunspot against the black of space, isolated from the sun, and it would glow white hot, brighter than an arc welder. And it's huge. A single sunspot can be larger than Earth. The smaller ones might be only a few thousand kilometers across, still larger than most countries. The bigger ones can be 50,000 kilometers across, or more, large enough to swallow several Earths. The largest sunspot ever recorded had an area of about 18 billion square kilometers, more than 15 times the entire surface area of Earth. You could fit more than 130 Earths across its diameter. When Galileo first observed sunspots in 1610 with his primitive telescope, it was revolutionary. For centuries, the prevailing Aristotelian view held that the heavens were perfect and unchanging. The celestial realm was fundamentally different from the corrupt, changeable Earth. The sun and planets were perfect crystalline spheres. But here was proof. The sun had blemishes. It had features. It had activity. It had weather. And those spots moved across the face of the sun, proving that the sun rotated. They appeared and disappeared, showing that the sun changed over time. The heavens were not eternal and perfect after all. What causes sunspots? Magnetic fields. When a strong magnetic field rises through the photosphere and emerges at the surface, it suppresses the normal convection of hot plasma. The magnetic field lines are like invisible ropes under tension, and plasma has difficulty crossing them. This inhibits the flow of heat from the interior. The area cools slightly, just enough to appear darker. It's like pressing down on a pot of boiling water. The bubbling stops where you press. Sunspots have internal structure. The dark central area is called the umbra, Latin for shadow, where the magnetic field is strongest and most vertical. Surrounding the umbra is the penumbra, with a distinctive radial, filamentary structure where the field begins to arc outward. Sunspots usually appear in pairs or groups because magnetic field lines form loops. One sunspot marks where the field emerges from the interior. The other marks where it descends back down. Between them, an arch of magnetism curves through the corona. Sunspots come and go. They appear, grow, sometimes merge with other spots, reach maximum size, then gradually decay and fade away. And their numbers follow a rhythm, cycle that lasts about 11 years. During solar minimum, the sun's surface is quiet. Few sunspots. Sometimes days go by without a single spot visible. The sun looks calm, almost boring. But during solar maximum, the sun is covered in sunspots. Dozens at a time. Clusters scattered across both hemispheres. The magnetic field is at its most chaotic. The star is restless, active, and that's when the storms begin. There's something that builds even in the images, a sense of gathering energy. The calm is temporary. The sunspots aren't just marks, they're warnings. They're the visible manifestation of energy accumulating beneath the surface. Because where there are sunspots, there are flares. Imagine two magnetic field lines, twisted and stretched, running parallel to each other just above the surface of the sun. They're carrying electric currents. They're under enormous tension. They're storing incredible amounts of energy. Plasma flows along them, trapped by their structure, heating up as it's compressed and accelerated. The field lines are slowly being pushed together by the motion of the photosphere beneath them, by the shifting and churning of the convection zone, by the complex dance of magnetic structures in the corona. And then, suddenly, they touch. The topology changes in an instant. The field lines break. They reconnect in a new configuration. And in that instant, all the energy they were holding is released. Not slowly, not gradually, instantly. This is a solar flare, a sudden, brilliant explosion of light and radiation. It flashes across the surface of the sun in minutes, releasing as much energy as billions of nuclear bombs, detonating at once. In the largest flares, the energy release can be equivalent to tens of billions of megatons of TNT, many times the entire nuclear arsenal of humanity detonated simultaneously. The temperature in the reconnection region spikes to tens of millions of degrees, hotter than the core of the sun itself. X-rays flood outward. Entire regions of the sun brighten dramatically, as if a switch has been flipped. The process is called magnetic reconnection. When the field lines snap and reconnect, they accelerate particles to nearly the speed of light. Electrons and protons are flung outward in jets. The plasma trapped in the magnetic loops is suddenly heated to extreme temperatures. It radiates across the entire electromagnetic spectrum. Radio waves, visible light, ultraviolet, X-rays, even gamma rays. If you were watching from space, if you had a telescope pointed at the sun at the exact right moment, you'd see it. A white hot point of light, blooming on the surface, expanding, flaring, and then fading, leaving the sun looking almost the same as before. But the light doesn't stop at the sun. It travels at the speed of light, across 150 million kilometers of space. 8 minutes later, it reaches Earth. And if the flare was strong enough, we notice. The Earth's dayside upper atmosphere, the ionosphere, is suddenly bombarded with X-rays and extreme ultraviolet radiation. This ionizes the atmosphere, disrupting the D layer that normally reflects radio waves. Radio communications on the dayside of Earth go silent. High-frequency signals used by aircraft, ships, and ham radio operators scatter and distort. Aircraft lose contact with ground control. It's called a radio blackout, and during strong flares, it can last for hours. Satellites experience glitches. Their electronics are bombarded with high-energy particles and X-rays. Solar panels degrade slightly from radiation damage. Memory chips experience bit flips, single-event upsets where radiation flips a bit from 0 to 1. Star trackers are temporarily blinded by the intense light. Astronauts aboard the International Space Station retreat to shielded areas to avoid radiation exposure. During the famous Halloween storms of October 2003, astronauts reported seeing flashes of light, even with eyes closed, caused by energetic particles passing through the eyeball and triggering photoreceptors directly. All of this from a flash of light that lasted minutes. Solar flares are classified by intensity. C-class flares are small to medium. M-class flares are medium. They can cause brief radio blackouts. X-class flares are the monsters, 10 times stronger than M-class. The strongest ever reliably recorded was an X-28 event in November 2003. But even that was an underestimate. The detectors were saturated. The true intensity may have been X40 or even X45. If a flare that strong occurred today, aimed directly at Earth, every satellite on the day side would be affected. GPS would fail globally. Communication networks would go down. Radiation exposure for astronauts would be life-threatening. But as violent as solar flares are, as powerful and sudden, they are not the most dangerous thing the sun can do. Because sometimes the sun doesn't just release light, it releases matter. This is the moment. This is the storm bigger than planets. A coronal mass ejection, CME, is not a flash of light. It's not radiation traveling at light speed and disappearing 8 minutes later. It is a physical eruption, a real, tangible explosion of matter into space. Imagine a massive structure in the sun's corona, billions of tons of plasma held in place by magnetic field lines. It's been there for days, gradually building up stress as the magnetic fields beneath it twist and reconfigure. And then, suddenly, the magnetic structure fails. The field lines snap. they reconnect, and the entire structure, billions of tons of plasma, is flung into space. Literally, billions of tons. The mass of a small mountain launched into space in minutes. Typical CMEs carry 10 to 100 billion tons of mass, material that was part of the sun's atmosphere just moments before. The CME expands outward like a bubble. It grows as it travels. It moves at speeds up to 3,000 kilometers per second. That's 1% the speed of light. Fast enough to cross the distance from the sun to Earth in 15 to 72 hours. And as it expands, it gets enormous. Larger than the sun itself. Larger than Jupiter. A cloud of charged particles and twisted magnetic fields, spreading across tens of millions of kilometers of space, barreling through the solar system like a tsunami made of magnetized plasma. If you could watch with instruments sensitive to the right wavelengths, like the coronagraphs that block the sun's bright disk to reveal the faint corona, you'd see a piece of the star's atmosphere tear free and bloom outward in a halo of light. The corona brightens, material streams away. A bubble of plasma glowing faintly expands into space like a wave spreading from a splash. This is not fire. This is not an explosion in the traditional sense. This is the sun exhaling a storm. A portion of its own atmosphere torn away by magnetic forces and hurled into space, carrying with it a frozen-in snapshot of the sun's magnetic field at that moment. A magnetic flux rope, twisted and coiled, embedded in billions of tons of plasma. And if Earth happens to be in the way, if the trajectory lines up, that storm will hit us. Not every CME is aimed at Earth. Most aren't. But the sun ejects CMEs continuously. During solar maximum, several per day. Over the course of a solar cycle, thousands. And some of them are aimed right at us. When a full halo CME appears in the coronagraph images, expanding in all directions like a ring, it's a warning. It means the eruption is heading either toward or away from Earth. And when spacecraft at the L1 Lagrange point detect the shockwave arriving, we have maybe 30 to 60 minutes of final warning before impact. All you can do is watch it come. Earth has a shield, the magnetosphere, a magnetic bubble generated by our planet's molten iron core, stretching tens of thousands of kilometers into space on the day side and even farther on the night side, forming a long magnetotail that extends beyond the orbit of the Moon. This magnetic field is not optional. It's essential for life. The magnetosphere deflects the solar wind, the constant stream of charged particles flowing from the sun at 400 to 500 kilometers per second, every second, carrying about 1 million tons of plasma outward. Without this shield, the solar wind would slowly strip away Earth's atmosphere over millions of years. We know this happened to Mars. Mars once had a thicker atmosphere and liquid water, but Mars lost its global magnetic field billions of years ago, when its core cooled and solidified. Without protection, the solar wind stripped away most of its atmosphere. What remains is a thin wisp, less than 1% the density of Earth's atmosphere. The surface pressure is barely above the triple point of water. Mars became a frozen desert. Earth's magnetosphere protects us. It creates a cavity in space where our atmosphere can exist. But when a coronal mass ejection strikes, the magnetosphere doesn't just deflect it, it compresses. The CMI slams into Earth's magnetic field like a tsunami hitting a seawall. The shockwave arrives first, a sharp, sudden jump in solar wind speed, density, and magnetic field strength, detected by spacecraft at L1 about an hour before it reaches Earth. Then the main body arrives, billions of tons of magnetized plasma, pushing against Earth's magnetosphere with immense pressure. The magnetopause, the boundary between Earth's magnetic field and space, is pushed inward. Under normal conditions, it sits at about 10 Earth radii on the day side. During a strong CME impact, it can be compressed down to 6 or 7 Earth radii, sometimes even to 4 or 5 during extreme events. Satellites at geosynchronous orbit, normally well inside the magnetosphere, can suddenly find themselves outside, directly exposed to the solar wind. On the night side, magnetic field lines are stretched farther. Magnetic energy accumulates in the magnetotail like a drawn bow. And then, inevitably, the field lines snap. Magnetic reconnection occurs in the magnetotail. Field lines from the northern and southern lobes connect across the equatorial plane. When they do, they release energy and funnel charged particles earthward, down toward the poles. The particles, electrons and protons, spiral along the magnetic field lines, descending into the upper atmosphere at altitudes of 100 to 500 kilometers. And when they collide with oxygen and nitrogen molecules, something beautiful happens. Light, the aurora. Curtains of green and red and violet rippling across the night sky, dancing in real time as the solar wind pours in. The green comes from oxygen at lower altitudes, around 100 to 250 kilometers. The red comes from oxygen at higher altitudes, 200 to 350 kilometers, from a transition that takes up to 2 minutes, only possible where the atmosphere is thin enough. The blue and purple come from nitrogen molecules. People in Alaska, Norway, Canada, Iceland see them regularly. The aurora borealis in the north, the aurora australis in the south. But during a strong geomagnetic storm, the auroral oval expands dramatically. Auroras spread to lower latitudes. During severe storms, they can be visible from the northern United States, from the Mediterranean, from northern Australia. During the Carrington event of 1859, the most powerful geomagnetic storm in recorded history, auroras were visible from the Caribbean and Hawaii, practically at the equator. It's one of the most stunning sights in nature, but it's also a symptom. Because while the aurora dances, while people stand outside in awe watching the light show, other things are happening. Less visible, less beautiful, more dangerous. Satellites in orbit are being bombarded with radiation. Electronics glitch, memory chips experience bit flips. Some satellites go into safe mode, shutting down non-essential systems. A few might be permanently damaged, their circuits fried, their missions ended. GPS signals degrade or fail entirely. The ionosphere becomes disturbed, chaotic. Radio waves passing through it are delayed, refracted, scattered unpredictably. GPS receivers calculate positions based on precise timing of signals from multiple satellites. When the ionosphere is disturbed, those timing calculations go wrong. Your GPS might show you in the wrong place. It might lose signal completely. And GPS isn't just navigation. Power grids, financial networks, and telecommunications all rely on GPS timing signals. If GPS fails, these systems are disrupted too. Aviation is affected. Airlines reroute polar flights to lower latitudes, adding hours to journeys. Passengers and crew on polar routes receive elevated radiation doses during severe storms. And on the ground, power grids begin to feel the strain. When the magnetosphere compresses and fluctuates, it induces electrical currents in anything conductive on Earth's surface. Power lines, pipelines, railway tracks. These are called geomagnetically induced currents, GICs. They flow through the power grid uninvited, driven by the changing magnetic field overhead. Transformers are designed to handle alternating current at a specific frequency, 50 or 60 Hz. But GICs are quasi-direct currents. They cause the transformer core to saturate. When saturated, transformers overheat. They draw excessive current, they vibrate and buzz. the insulation begins to degrade. If the GICs are strong enough and last long enough, transformers can fail catastrophically. Insulation melts, windings short circuit. In extreme cases, they catch fire. They explode, spewing thousands of gallons of mineral oil. And transformers are not easy to replace. They're massive. Some weigh hundreds of tons. They're expensive. High-voltage transformers can cost millions of dollars each. They're custom-built for specific locations. Lead times for manufacturing a new transformer can be more than a year. If hundreds of them failed at once across a continent, the grid would be crippled for months, possibly years. It has happened before. September 1st, 1859. Richard Carrington, a British astronomer, was in his private observatory, sketching sunspots through his telescope. It was part of his daily routine. Just before noon, he saw something extraordinary. Two bright patches of intensely white light appeared within a large sunspot group. Blindingly bright, visible against the already bright solar surface. They moved across the sunspot group. They pulsed and flared. They persisted for about 5 minutes, then faded away. Carrington had just witnessed a massive solar flare, the first one ever observed by a human being. He immediately realized it was significant. He rushed to find a witness, but by the time he returned, the flare had faded. 17 hours later, the CME arrived. Telegraph systems around the world went haywire. Operators reported sparks flying from their equipment. Telegraph keys glowed red hot. Papers on desks caught fire. Some operators were physically shocked. Electrical currents flowing through the lines were strong enough to be felt, strong enough to be dangerous. Some operators found they could disconnect their batteries entirely and still send messages, powered only by the currents induced by the geomagnetic storm. The Earth itself had become a battery, and the auroras were unlike anything seen before or since. They were visible from the Caribbean, from Hawaii, from Colombia, near the equator. Reports came in from Australia, from southern Africa, from across South America. People in the Rocky Mountains woke up at 2 or 3 in the morning thinking it was dawn. The sky glowed red and green and violet, bright enough to read a newspaper by. Miners started making breakfast thinking morning had come. In Boston, New York, Paris, London, places where auroras are essentially never seen, the sky was ablaze with colored light. One observer in Havana, Cuba, wrote that the aurora was so brilliant that at 1 o'clock in the morning, ordinary print could be read by its light. It was a global event. The entire planet was engulfed in the storm. At the time, humanity barely had electrical infrastructure. The telegraph was the most advanced technology. The damage was dramatic, but minimal. Some burnt wires, some confused operators, some fires. But if it happened today, we are so much more fragile now. The modern world doesn't just use electricity, it is electricity. Every system, every infrastructure, every service depends on it. Banking, communication, transportation, the internet, supply chains, hospitals, water treatment, agriculture, all of it runs on electricity. And the power grid is vulnerable in ways the telegraph system never was. A Carrington-level event today would induce massive currents in power grids across entire continents. High-voltage transformers at vulnerable nodes, particularly at high latitudes where the magnetic field changes are strongest, would begin to overheat within minutes. Circuit breakers would trip. Grid operators would try to shed load. But the GICs would be too strong, too widespread. Transformers would begin to fail. Not 1 or 2, dozens, hundreds. And we don't have spare transformers. Not enough anyway. High-voltage transformers are custom-designed and built to order. They're manufactured by a small number of specialized companies. Lead times are typically 12 to 18 months. If hundreds fail simultaneously, there's no way to replace them quickly. The blackouts would last. Not hours, not days, weeks, months. In some areas, potentially years. And a modern society cannot function without electricity for extended periods. Within days, the impacts would cascade. No electricity means no refrigeration. Supermarkets lose their cold. Storage. Food spoils within days. Supply chains, which depend on just-in-time delivery, break down entirely. No electricity means no fuel pumps. Even if gas stations have fuel in their underground tanks, they can't pump it without power. Transportation grinds to a halt. Communication networks fail. Cell towers have backup batteries, but they only last hours. Once those die, cell phones stop working. The internet, the backbone of modern commerce, communication and coordination, fails. Data centers have generators, but without fuel deliveries, they go dark. Financial systems freeze. ATMs don't work. Credit card transactions can't be processed. Stock markets close. Banking grinds to a halt. The economy stops. Water treatment plants shut down. Many depend on electric pumps. Without power, clean water stops flowing. Sanitation systems fail. Hospitals run on backup generators. They triage, treating only the most critical cases, but their generators need fuel. After a week or two, the generators run dry. Life support systems fail. People die. A 2008 report by the National Academy of Sciences estimated that a severe geomagnetic storm could cause $1 to $2 trillion in damage in the first year alone, with recovery taking 4 to 10 years. More recent estimates are higher, accounting for cascading failures in interconnected systems. And this isn't science fiction. In July 2012, a massive CME erupted from the Sun, at least as powerful as the Carrington event, possibly stronger. If it had occurred a week earlier when that region of the Sun was facing Earth, it would have hit us directly. Instead, it missed. It passed through Earth's orbit after we'd moved on. A week's difference. That's all that stood between us and potential catastrophe. The Sun doesn't care. It has no intent, no malice. It's just doing what stars do. The storm is built into its nature. Magnetic fields twist. Energy accumulates. Eventually, it releases. But we're not helpless. We've learned to watch. Space weather forecasting is a real field. Satellites monitor the Sun constantly. The Solar Dynamics Observatory, the Solar and Heliospheric Observatory, DSCOVR at the L1 point. When they detect an Earth-directed CME, alerts go out to satellite operators, utility companies, airlines. It's not perfect. Predictions have uncertainties, arrival times can be off by many hours. But it's something. And we're improving. And we've gone further than just watching. In 2018, humanity did something unprecedented. We sent a spacecraft into the Sun's atmosphere. The Parker Solar Probe. Named after Eugene Parker, the astrophysicist who first predicted the existence of the solar wind in 1958. His ideas were controversial at the time. One reviewer called his paper impossible and recommended rejecting it. But the journal editor overruled and published it. 5 years later, the Mariner 2 spacecraft confirmed Parker's prediction. The solar wind was real. Parker lived to see the spacecraft named after him, the first time NASA named a mission after a living person. He was 91 years old, standing at the launch site, watching his life's work vindicated in the most spectacular way possible. The Parker Solar Probe is about the size of a small car, and it's built to survive conditions no human-made object has ever faced. At the front, it carries a heat shield made of carbon composite foam, 12 centimeters thick. Behind that shield, the instruments stay relatively cool, around room temperature, about 30 degrees Celsius. but the shield itself endures temperatures exceeding 1,400 degrees Celsius during closest approach. Hot enough to melt steel, to vaporize aluminum, to turn most materials to gas. And it's fast. The fastest human-made object ever built. At its closest approach to the Sun, the Parker Solar Probe travels at over 700,000 kilometers per hour, about 195 kilometers per second. Fast enough to fly from New York to Tokyo in less than 1 minute. Fast enough to circumnavigate Earth in just over 3 minutes. The probe achieves this speed through gravity assists from Venus. It uses Venus's gravity to bend its trajectory and lose orbital energy, falling closer and closer to the Sun with each pass. 7 Venus flybys over the course of the mission, each one dropping its closest approach lower. And how close does it get? The probe dives to within 6.2 million kilometers of the Sun's surface. That might still sound far, but Mercury, the innermost planet, orbits at about 58 million kilometers. The Parker Solar Probe gets almost 10 times closer than that. Close enough to pass through the corona, the Sun's outer atmosphere. Close enough to measure the solar wind at its source. Close enough to fly through coronal mass ejections and solar storms. In April 2021, during its 8th solar flyby, the probe crossed the Alfvén surface, the boundary where the solar wind transitions from being controlled by the Sun's magnetic field to streaming freely into space. It became the first spacecraft ever to enter the Sun's atmosphere, the first to touch a star. Why would we risk such an expensive, complex mission? Because we need to understand. The Sun is not a solved problem. Fundamental mysteries remain. How does the corona get so hot? How do CMEs form and launch? How does the solar wind accelerate? These aren't just academic questions. Space weather is real weather. And if we're going to live as a technological civilization that depends on satellites and power grids, we need to predict it. The Parker Solar Probe is sending back data that's revolutionizing our understanding of the Sun. It has discovered switchbacks, sudden, large amplitude reversals in the magnetic field that zigzag back and forth. It has measured turbulence in the solar wind with unprecedented detail. It has sampled the corona directly, flying through the very processes that produce space weather. It's humanity's ambassador to the Sun, our way of saying, we're not content to watch from a distance anymore. We want to know what you are. And here's one of the biggest mysteries the probe is helping us solve. The Sun's surface, the photosphere, is about 5,500 degrees Celsius. The corona, the atmosphere above it, is over 1 million degrees. The atmosphere is hotter than the surface, by a factor of 200 or more. That should be impossible. Heat doesn't flow from cold to hot, not without energy input. It violates our everyday experience of how heat works. It's like standing next to a candle and feeling the air above the flame is somehow hundreds of times hotter than the flame itself. And yet, that's what's happening on the Sun. This is called the coronal heating problem, and it's been one of the great unsolved mysteries of solar physics since it was discovered in the 1940s. When spectroscopic observations revealed that the corona was emitting light characteristic of extremely high temperatures. Highly ionized iron atoms that can only exist at temperatures above 1 million degrees. Scientists were baffled. The Sun generates energy in its core through fusion. That energy moves outward through radiation and convection. By the time it reaches the photosphere, it has cooled to 5,500 degrees. There's no obvious source of additional heat in the corona, and yet something is pumping enormous amounts of energy into that tenuous atmosphere. Scientists have proposed several mechanisms. The first candidate is Alfvén waves, magnetic waves that ripple through the plasma, predicted by Swedish physicist Hannes Alfvén in 1942. He later won the Nobel Prize for his work. Alfvén waves are generated by the turbulent motion of plasma in the Sun's convection zone. Imagine the granulation cells we discussed, those country-sized pockets of plasma churning up and down. As they move, they shake the magnetic field lines threading through them. Those field lines vibrate, and the vibrations propagate upward as waves carrying energy. When Alfvén waves reach the corona, they can dissipate, releasing their energy as heat. The mechanism is complex. The waves can interact with each other, become turbulent, cascade to smaller scales, and eventually convert their energy into thermal motion of particles. The Parker Solar Probe has detected Alfvén waves in abundance. In 2019, the probe observed something extraordinary: large amplitude switchbacks in the magnetic field, sudden reversals where the field flips direction by nearly 180 degrees, then flips back. These switchbacks appear to be signatures of powerful Alfvén waves generated near the Sun's surface. Some of these waves carry enough energy to heat the corona, if they dissipate properly. The second candidate is nanoflares, tiny explosions constantly sparking across the Sun's surface and in the corona. This idea was proposed by Eugene Parker in 1988. Each nanoflare releases a tiny amount of energy, perhaps 10 to the power of 24 ergs. A large solar flare releases 10 to the power of 32 ergs. So a nanoflare is about 1 billion times weaker than a major flare. But if there are billions or trillions of them happening constantly throughout the corona, they could collectively heat it to the observed temperatures. Nanoflares would be caused by magnetic reconnection on small scales. The Sun's magnetic field is never still. It's constantly being shuffled, twisted, reconfigured by the motion of plasma in the photosphere. Field lines are always tangling and reconnecting. Each reconnection event releases a small burst of energy, heating the local plasma. The challenge is observational. Individual nanoflares are too small and too brief to observe directly with current instruments, but their collective signature might be detectable in the statistical properties of coronal emission. The third candidate involves magnetic reconnection and turbulent dissipation in current sheets throughout the corona. Where field lines of different orientations come close together, thin current sheets form, regions of enhanced dissipation where magnetic energy is converted to heat. The idea is that the corona is filled with a complex web of these sheets, constantly forming, evolving, and releasing energy. The truth is probably all three working together. Different mechanisms may dominate in different regions. Alfvén waves might heat the fast solar wind streaming from coronal holes. Nanoflares might heat closed field regions over active areas. Turbulent dissipation might contribute everywhere. The Parker Solar Probe is designed to answer these questions by flying through the corona and measuring directly. Early results suggest that all three mechanisms are at work. Alfvén waves have been detected with amplitudes large enough to carry the required energy. Switchbacks might be signatures of reconnection events. Turbulence in the solar wind cascades across a wide range of scales. But the full picture is still emerging. The probe will continue making closer and closer passes through 2025 and beyond, eventually reaching within 6.1 million kilometers of the surface, passing through the hottest parts of the corona. And maybe then, finally, we'll solve the mystery. But the fact that we still don't have a complete answer, that this fundamental question about our own star remains open after 8 decades of study, should tell you something profound. The Sun is not a solved problem. It is not simple. It is not fully understood. Despite being the closest star, despite being studied more intensely than any other astronomical object, despite centuries of observation and decades of space missions, the sun still keeps secrets. It is still teaching us. And every time we think we've figured something out, we discover a new layer of complexity, a new mystery beneath the surface. The corona is just one example. Why does the solar wind accelerate? How are energetic particles accelerated to near-light speeds during flares? What determines the solar cycle's amplitude? Why does the cycle sometimes weaken or disappear, as during the Maunder minimum of the 1600s? We don't fully know. The sun is a laboratory for plasma physics, magnetohydrodynamics, turbulence, magnetic reconnection, wave-particle interactions, processes that occur throughout the universe, from Earth's magnetosphere to the jets of black holes to the interstellar medium. By studying the sun, we're not just learning about our star. We're learning about the fundamental physics that governs the cosmos. Let us return, for a moment, to scale, because our minds truly cannot hold it without repetition, without being brought back to it again and again from different angles. The sun is 1.4 million kilometers in diameter. Let that number settle. 1.4 million. If you could drive a car at highway speed, say 100 kilometers per hour from one side of the sun to the other, the journey would take more than 580 days. Driving non-stop, 24 hours a day, 7 days a week, for more than a year and a half. And that's just across its diameter, not even around it. The circumference of the sun is about 4.4 million kilometers. At highway speed, driving around the equator of the sun would take more than 5 years. Continuous, uninterrupted driving for 5 years. Earth, by comparison, is 12,700 kilometers in diameter. You could drive across the diameter of Earth in about 5.5 days at highway speed. The difference in scale is staggering. But the sun isn't just large. It's massive in ways that go beyond physical size. The sun's mass is about 2 × 10 to the power of 30 kilograms. That's 2 non-Illian kilograms. 2 non-Illian kilograms. A number that has no intuitive meaning to the human mind. Let's try to find meaning another way. The sun is so massive that it shapes the orbits of objects billions of kilometers away. Pluto, orbiting at an average distance of about 5.9 billion kilometers, is still gravitationally bound to the sun. It still orbits. It still follows the curve of space-time that the sun creates around it. Even beyond Pluto, in the distant Kuiper belt, in the scattered disk, in the theorized Oort cloud, all of it orbits the sun. Objects that are light years away in some models are still gravitationally connected to this star. The sun's gravity governs all of it. It curves space. Everything in the solar system lives in the gravitational well the sun creates. And all that mass is active. All that material is in motion, churning, rotating, convecting, generating magnetic fields, erupting. The sun is not a passive backdrop for our solar system. It is an active, dynamic, violent engine that shapes the environment of every planet, every moon, every asteroid, every comet that orbits it. We tend to think of space as empty, cold, quiet, and in many ways it is. But the space between the planets is not truly empty. It's filled with the sun's atmosphere, the solar wind, the solar magnetic field, the occasional blast of a coronal mass ejection. Our solar system is inside the sun's weather, just as surely as a city is inside Earth's weather. The solar wind is the sun's constant exhalation. A continuous stream of charged particles, mostly electrons and protons, flowing outward from the sun's corona at 400 to 800 kilometers per second, carrying about 1 million tons of plasma outward every second. Every second. 1 million tons of material leaving the sun every second, flowing outward through the solar system, past the planets, past the Kuiper belt, all the way to the heliopause, the boundary between the heliosphere and interstellar space, at about 120 astronomical units from the Sun. That's 120 times the Earth-Sun distance, about 18 billion kilometers. The Voyager 1 spacecraft launched in 1977 and now the most distant human-made object ever crossed the heliopause in 2012. It took more than 35 years of travel at about 17 kilometers per second to reach the edge of the Sun's influence. That's the scale of the heliosphere. The solar wind isn't uniform. It varies in speed, density, and magnetic field strength. There are fast streams and slow streams. The fast streams, typically 600 to 800 kilometers per second, come from coronal holes, regions of open magnetic field where the solar wind can escape freely. The slow streams, around 300 to 400 kilometers per second, come from the regions around the Sun's equator. When a fast stream catches up to a slow stream, they interact. The fast stream pushes into the slow stream, creating compressed regions called stream interaction regions, or corrotating interaction regions. These are persistent features that rotate with the Sun, creating a periodic pattern of enhanced solar wind that Earth passes through roughly every 27 days as the Sun rotates. These interaction regions can cause moderate geomagnetic storms, not as severe as CME impacts, but significant, enough to affect satellites and cause auroras at high latitudes. But the solar wind isn't just a hazard, it's also a tracer, a way for us to measure what the Sun is doing. By studying the solar wind's properties, its speed, density, temperature, composition, magnetic field, we can learn about the processes that produced it in the corona. The Parker Solar Probe's measurements of the solar wind close to the Sun are revealing these connections in unprecedented detail. The solar wind also shapes the comet tails we see from Earth. A comet has two tails, a dust tail, blown back from the comet by radiation pressure, and an ion tail, blown directly away from the Sun by the solar wind. The ion tail always points directly away from the Sun, regardless of the comet's direction of travel. Ancient observers knew about comet tails but had no idea they were being blown by a wind from the Sun. That understanding had to wait for the space age. And the solar wind compresses the magnetospheres of planets that have them: Earth, Jupiter, Saturn, Uranus, Neptune, creating the magnetotails we discussed earlier. It shapes the environment of every planet in the solar system. Our star breathes and the entire solar system breathes with it. We've talked about sunspots, flares, and CMEs. But there's another spectacular feature of the Sun that deserves its own moment: prominences. A solar prominence is a large, bright, relatively cool structure extending outward from the Sun's surface into the corona. They're suspended in the corona by magnetic field lines, held up against gravity by magnetic pressure. Prominences can be enormous. Large ones extend hundreds of thousands of kilometers above the surface, lengths comparable to the diameter of Earth multiplied by 10 or more. They contain plasma that is much cooler and denser than the surrounding corona, typically around 10,000 degrees, compared to the million-degree corona around them. Prominences are visible in specific wavelengths of light. In hydrogen alpha light, a deep red wavelength emitted by hydrogen atoms, they appear as bright, glowing features above the Sun's limb. On the disk of the Sun, they appear dark against the bright photosphere and are called filaments. Prominences can be stable for days, weeks, even months. They form when magnetic field lines create a hammock-like structure, a dip in the field lines where cool, dense plasma can accumulate and be supported against gravity. They are dynamic. Plasma streams along the field lines. Small-scale motions constantly churn the material inside. Waves propagate along the prominence, and sometimes they erupt. When a prominence becomes unstable, when the magnetic field that supports it is disrupted by changes in the surrounding corona, it can suddenly erupt outward. The plasma that was contained in the magnetic hammock is flung into space. Prominence eruptions are often accompanied by CMEs. The erupting prominence can be seen in coronagraph images, a bright, twisted structure moving outward with the expanding CME bubble. In fact, many CMEs include an erupting filament as a core component, the bright, twisted flux rope at the center of the CME. Watching a prominence erupt in slow motion, in time-lapse videos made from sequences of observations, is one of the most spectacular sights in solar astronomy. The structure quivers, it rises slowly, plasma streams along the field lines, and then, suddenly, it breaks free. It launches outward, twisting, unraveling, becoming part of the expanding CME. These eruptions remind us that the Sun's atmosphere is never truly at rest. Even in regions that look stable, energy is accumulating. Magnetic tension is building. Eventually, something always gives. The 11-year solar cycle is one of the most important and most studied patterns in solar physics. But it's also one of the least well understood at a fundamental level. We know what happens during the cycle. Sunspot, numbers rise and fall. Magnetic activity waxes and wanes. The Sun's magnetic poles flip every 11 years, completing a 22-year Hale cycle. But we don't fully understand why it lasts 11 years. Why not 5 years? Why not 20? What determines the period? The basic mechanism involves the interaction between differential rotation and the dynamo. Differential rotation stretches the poloidal field, the north-south dipole field, into a toroidal field, wrapped around the Sun's interior. Convection and the Coriolis effect then amplify this toroidal field and tilt it back toward a poloidal orientation. This is the alpha-omega dynamo, first described mathematically in the 1950s. In this model, the 11-year cycle emerges from the timescales of the dynamo process, how long it takes for the field to be stretched, amplified, and transformed. But the exact timescale depends on properties of the solar interior that are difficult to measure directly. We observe the cycle through its surface manifestations, sunspots, flares, CMEs. But the magnetic field is generated deep in the convection zone, near the tachocline. The surface features are the tip of the iceberg. Helioseismology, studying the Sun by analyzing sound waves that propagate through its interior, similar to how seismologists study Earth's interior using earthquake waves, has given us some insight. The Sun rings like a bell. Surface oscillations driven by convective turbulence propagate downward as pressure waves and can be detected back at the surface after they bounce around the interior. By analyzing the frequencies and travel times of these waves, helioseismologists have mapped the Sun's internal structure and rotation profile. They've confirmed the differential rotation. They've detected large-scale flows, the meridional circulation, a slow flow from the equator to the poles at the surface, and from the poles to the equator deep in the convection zone. This meridional circulation plays a role in the solar cycle too. It carries magnetic flux poleward at the surface, where it cancels the old magnetic field and builds up the new. And it carries material downward at the poles and equatorward at the base of the convection zone, bringing magnetic flux back toward the equator. The speed of the meridional circulation affects the solar cycle period. If the circulation is faster, the cycle is shorter. If it's slower, the cycle is longer. Variations in the circulation speed might explain some of the variability in cycle amplitude and period that we observe. But we don't have a complete predictive model. We can't reliably predict the strength of the next solar cycle years in advance. We get better at it. The predictions for cycle 25 were more accurate than those for cycle 24, but there's still significant uncertainty. The sun keeps surprising us. Cycle 24 was unexpectedly weak. The current cycle 25 appears to be stronger than predicted. Grand minima, like the Maunder. Minimum occur, but their triggers are not well understood. Understanding the solar cycle isn't just an academic exercise. It has practical importance. A stronger solar cycle means more frequent and more powerful storms, more CMEs, more X-class flares, more space weather events that can affect satellites and power grids. If we could predict the solar cycle accurately, we could prepare better. We could know years in advance when the most dangerous period of space weather was approaching. That's one of the goals of ongoing research. And it's a goal we haven't yet reached. We've talked about the sun as our star, our local furnace, the source of life on Earth. But let's zoom out. Let's think about the sun in the context of the universe. The sun is a G-type main sequence star, also called a yellow dwarf. This classification tells us several things. It's a main sequence star, meaning it's in the stable, hydrogen-burning phase of its life. It's a G-type, meaning its surface temperature is between about 5,200 and 6,000 Kelvin, the cooler end of the middle range for main sequence stars. In the cosmic zoo of stars, the sun is fairly average. There are stars that are more massive, blue giants and supergiants that burn bright and fast, living only millions of years. There are stars that are less massive, red dwarfs that burn dim and slow, living for trillions of years. The sun is in between. About 7% of the stars in the Milky Way are G-type stars like the sun. The galaxy contains about 250 billion stars, so there are roughly 17 billion G-type stars in the Milky Way alone. Not all of them have planets. Not all of those planets are in the habitable zone, but the sheer number of G-type stars suggests that there could be many Earth-like worlds orbiting sun-like stars across the galaxy. The sun is about 4.6 billion years old, roughly middle-aged for a star of its type. G-type stars have main sequence lifetimes of about 10 billion years. The sun has roughly 5 billion years left before it exhausts its hydrogen fuel. When that happens, it will swell into a red giant. It will expand to perhaps 100 to 200 times its current radius. Mercury and Venus will be consumed. Earth may be swallowed too, or may just barely survive. But the oceans will have boiled away and the atmosphere will have been stripped long before the sun physically expands to that size. Eventually, the sun will shed its outer layers in a beautiful planetary nebula, and the core will remain as a white dwarf, a dim, dense remnant about the size of Earth, slowly cooling over billions of years. The sun will die, as all stars die, but right now, it's alive, in the middle of its life, burning, churning, storming, and we're here to witness it. That's remarkable. Out of all the billions of years the sun has existed and will exist, we happen to be alive now. We happen to have developed the technology to study it. We happen to have sent spacecraft to touch it. We live at an extraordinary moment, not just in human history, but in the sun's history. A moment when a species on one of the sun's planets has become curious enough to ask, "What are you, really?" and advanced enough to go find out. That's worth celebrating. As humanity prepares to return to the moon and eventually send astronauts to Mars, space weather becomes not just a technological concern, but a life safety issue. On Earth, we're protected by two layers, our atmosphere and our magnetosphere. Together, they block most of the harmful radiation from solar flares and cosmic rays. Even at the highest altitudes commercial aircraft fly, about 12 kilometers, the atmosphere provides significant shielding. Astronauts at the International Space Station at 400 kilometers altitude are still inside the magnetosphere and have significant protection, though not as much as on Earth's surface. But beyond the magnetosphere, in cislunar space, on the lunar surface, on the way to Mars, astronauts are fully exposed to the space radiation environment. They have only the shielding provided by their spacecraft and spacesuits, and that shielding is limited by weight constraints. A major solar particle event, a strong flare accompanied by a CME, can expose unshielded astronauts to dangerous, potentially lethal doses of radiation. The particles, mostly protons, can penetrate thin spacecraft walls and damage cells, particularly rapidly dividing cells like those in the bone marrow and intestinal lining. The August 1972 event, a massive solar proton event that occurred between the Apollo 16 and Apollo 17 lunar missions, would have been lethal for astronauts on the lunar surface with only their spacesuits for protection. Fortunately, no astronauts were outside at the time. For future lunar missions, particularly longer surface stays, radiation shelters will be essential. Deep, robust shelters that astronauts can retreat to during solar storm events. Underground habitats, or habitats, covered with thick regolith, or water-walled shelters. For Mars missions, the situation is even more challenging. The trip to Mars takes 6 to 9 months, one way. During that time, astronauts are exposed to the galactic cosmic ray background, high-energy particles from outside the solar system that the sun's magnetic field partially shields us from, as well as potential solar particle events. Current estimates suggest that a round trip to Mars would expose astronauts to roughly the lifetime career limit of radiation for NASA astronauts. Space weather prediction becomes literally vital in this context. If we can predict a major solar particle event days or weeks in advance, astronauts can take shelter before the particles arrive. If we can't, they might be caught outside during an EVA when a major flare erupts. This is one of the driving motivations behind solar physics research. It's not just about protecting satellites and power grids. It's about protecting human lives in space. It's about enabling the expansion of humanity beyond Earth. Understanding the sun isn't just scientific curiosity. It's a prerequisite for becoming a spacefaring civilization. One of the most powerful ways to understand the sun is to compare it to other stars, particularly stars that are similar to it, called solar analogues or solar twins. A solar twin is a star with nearly identical mass, age, chemical composition, and evolutionary state to the sun. Finding them requires precise spectroscopic measurements to determine temperature, surface gravity, and chemical abundances. Over the past few decades, astronomers have identified dozens of solar twins in our galactic neighborhood. Studying these stars tells us how the sun compares to similar stars. Is the sun unusually active, unusually quiet, typical? The results are reassuring in some ways and concerning in others. In terms of overall activity, the sun appears to be fairly typical for a star of its age and type. Its average magnetic activity, measured by the strength of emission in certain spectral lines, is unremarkable. But solar-type stars can produce superflares, flares much more powerful than any observed from the sun in historical times. The Kepler Space Telescope, which monitored hundreds of thousands of stars for brightness variations, detected superflares from many solar-type stars. These were events 10 to 10,000 times more powerful than the largest solar flares ever recorded. Does the sun produce such events? We have no historical record of them, but the sun's 11-year cycle means its activity varies, and geological records suggest that the sun may have been more active in the distant past. Radiocarbon dating of ancient trees, comparing carbon-14 levels in tree rings, has revealed sudden spikes in cosmic radiation, that could indicate massive solar particle events. One such event, dated to around 774 to 775 CE, left a clear signature in tree ring data from Japan, Germany, and the United States. The carbon-14 spike was much larger than what modern solar flares produce. It may represent a solar particle event 10 to 20 times stronger than any in the modern record. Another spike is recorded around 993 CE, and possibly others. This suggests that the Sun is capable of producing events significantly more powerful than anything we've experienced in the modern technological era. We've been measuring solar activity with instruments for only about 70 years. The Sun's historical record goes back 4.6 billion years. We might be living in a relatively quiet period. The big one might be coming. This isn't cause for panic, but it is cause for preparation, for taking space weather seriously, for hardening infrastructure, for developing better early warning systems. The Sun is old and familiar, but it's also capable of surprises. The Parker Solar Probe is transforming our understanding of the Sun, but it's not operating in isolation. A fleet of spacecraft is studying our star from multiple angles, and new observatories are being planned. The Solar Orbiter, launched by the European Space Agency in 2020, is doing something different from Parker. Instead of diving very close to the Sun, Solar Orbiter is tilting its orbit out of the ecliptic plane, out of the plane in which the planets orbit. This allows it to see the Sun's polar regions, which have never been observed up close before. The Sun's poles are important because the polar magnetic fields seed the next solar cycle. When the Sun's magnetic field reverses polarity at solar maximum, the new polarity begins at the poles and migrates toward the equator over the following years. By observing the poles directly, Solar Orbiter can see this process in action. Early results from Solar Orbiter have been spectacular. The spacecraft captured the first close-up images of campfires, small, intense brightenings near the solar surface that may be miniature flares or nanoflares, potentially contributing to coronal heating. These campfires are too small to see from Earth, but from Solar Orbiter's closer vantage point, they're visible, revealing the small-scale texture of the Sun's activity. On the ground, the Daniel K. Inouye Solar Telescope, DKIST, represents a revolution in ground-based solar observation. Located on the summit of Haleakala volcano in Hawaii at 3,000 meters altitude, DKIST has a 4-meter primary mirror, the largest solar telescope ever built. It can resolve features as small as 30 kilometers across on the Sun's surface. For comparison, features 100 kilometers across were state-of-the-art just a few years ago. First light images from DKIST, released in 2020, were stunning. They showed the solar surface in unprecedented detail, granulation cells with clear internal structure, sunspot umbras and penumbras with intricate filamentary detail, small-scale magnetic features that had previously been invisible. DKIST is particularly powerful because it can measure magnetic fields very precisely through spectropolarimetry, measuring the polarization of light to infer the direction and strength of the magnetic field. This capability will be crucial for understanding how energy is stored and released in the corona. The future holds more. The proposed multi-slit solar explorer, MUSE, would observe the Sun in multiple wavelengths simultaneously with unprecedented cadence, studying the dynamics of coronal heating in real time. The proposed space weather with quantitative solar imagery, SWIM mission, would provide better CME forecasting. The proposed Lagrange mission, led by ESA, would place a spacecraft at the L5 Lagrange point, trailing Earth in its orbit, giving us a side view of solar activity and better CME tracking. We're entering a golden age of solar physics. Multiple spacecraft and observatories coordinating observations covering different wavelengths and different vantage points will give us a comprehensive, three-dimensional view of the Sun and its activity. The mysteries we've discussed tonight, the coronal heating problem, the acceleration of the solar wind, the origin and prediction of CMEs, are all within reach of being solved in the coming decades. The Sun is giving up its secrets slowly, reluctantly, but inevitably. Carl Sagan, in his famous reflection on the Voyager 1 image of Earth from beyond the orbit of Neptune, called our planet a mote of dust suspended in a sunbeam. That sunbeam. That's what we've been talking about all along. Earth is a mote of dust. We are tiny, our history is brief, our troubles, as significant as they feel from inside, are small against the scale of the cosmos. But we're also extraordinary. We're the only place in the universe, as far as we know, where matter has looked back at the stars and wondered about them. We're the only place where the universe has become conscious of itself, where it has developed curiosity about its own nature. And we've aimed that curiosity at the Sun. We've built telescopes and sent spacecraft. We've decoded the messages hidden in sunlight. We've measured magnetic fields 150 million kilometers away. We've flown through the corona and tasted the Sun's atmosphere. We've done this not because we had to, not because we were forced, but because we wanted to understand. Because curiosity is one of the most human things there is. The Sun is dangerous. Its storms can disrupt our technology, endanger our astronauts, challenge our civilization. But the Sun is also the source of everything we have. Every calorie of food, every molecule of oxygen, every photon that has ever allowed a human eye to see. We owe our existence to this star, and we've spent our history trying to understand it. From the ancient sun worshippers who built Stonehenge, to the physicists who decoded nuclear fusion, to the engineers who built the Parker Solar Probe, humans have always looked at the Sun and asked, "What are you?" We're getting closer to the answer. The sky above us has never been empty. We have always been living inside a star's weather. And now, finally, we're starting to understand what that means. There is a moment, if you've ever watched a solar eclipse, when the moon slides perfectly in front of the Sun and the corona becomes visible to the naked eye. For a few minutes, perhaps 2 or 3, you can see what astronomers have been studying for centuries, the wispy, pearlescent halo of the Sun's outer atmosphere, stretching outward in streamers and plumes, glowing against the sudden darkened sky. Every star you can see at night has a corona too, but we're too far from those stars to see their coronas. Only our Sun is close enough that we can watch its atmosphere directly, that we can send spacecraft into it, that we can study it in detail. We are privileged to live around such a star. Not just because it keeps us warm and alive, but because it's close enough to study. Because it's our laboratory for stellar physics, for plasma physics, for space weather. What we learn about the Sun, we apply to other stars, to the heliospheres of other solar systems, to the environments of other potentially habitable worlds. When we study space weather from our Sun, we're also learning about the habitability conditions around other stars. Red dwarf stars, the most common type in the galaxy, are known to be extremely active, producing frequent and powerful flares that could be devastating for planets in the habitable zone. Does that mean those planets can't support life? Or does life find a way to adapt, to shelter underground, to develop protective mechanisms? We don't know yet. But studying how Earth life has survived in our star's weather gives us a framework for thinking about life elsewhere. The questions we're asking about our Sun are, in a sense, questions about life in the universe. Let's take a moment to appreciate the numbers, because they're almost unbelievable. The sun's luminosity, its total power output, is approximately 3.846 times 10 to the power of 26 watts. That's about 384.6 yottawatts, or 384.6 trillion watts. At Earth's distance from the sun, this spreads out over a sphere of radius 150 million kilometers. The area of that sphere is about 2.82 times 10 to the power of 23 square meters. Dividing the luminosity by the area gives the solar irradiance at Earth's distance, about 1,361 watts per square meter. This is called the solar constant. Earth's cross-sectional area, the area of the shadow it casts, is about 1.274 times 10 to the power of 14 square meters. Multiplying by the solar constant gives the total power Earth intercepts from the sun, about 1.74 times 10 to the power of 17 watts, 174 petawatts. That's about 9,600 times the total power currently used by human civilization. Of this intercepted energy, about 30% is immediately reflected back to space by clouds, ice, and the Earth's surface, Earth's albedo. The remaining 70%, about 122 petawatts, is absorbed by the atmosphere, oceans, and land. This absorbed energy drives all of Earth's weather, ocean currents, and climate. It powers photosynthesis, which supports essentially all life on Earth. The total power of all human civilization combined, all our electricity, all our burning of fossil fuels, all our nuclear power, is about 18 terawatts. The sun delivers more than 6,700 times that amount to Earth, and we only capture a small fraction of even that. If we could cover even a small percentage of Earth's surface with highly efficient solar panels, we could power civilization many times over. The energy is there, it's arriving every second. We just need to capture it. This is why solar energy is so compelling as a long-term solution for humanity's energy needs. The sun will continue to deliver this power for another 5 billion years. That's an essentially unlimited energy source from a human perspective. We live in the wealth of a star's energy, most of which we currently let pass through our fingers. There's a psychological phenomenon that makes understanding the sun and the cosmos in general genuinely difficult. It's not a lack of intelligence, it's a feature of how human minds work. We evolved on the African savanna. Our ancestors needed to track prey, avoid predators, recognize faces, plan for the near future. We evolved to be excellent at handling scales of meters to kilometers, time scales of minutes to years, quantities of 1 to maybe a few hundred. We did not evolve to intuitively grasp distances of 150 million kilometers, or masses of 2 times 10 to the power of 30 kilograms, or timescales of billions of years, or temperatures of 15 million degrees. These numbers are real. They describe reality accurately, but they don't feel real the way that 10 meters or 2 hours feels real. They live in the intellectual part of the brain, the prefrontal cortex, the analytical mind, rather than the visceral, emotional part that makes something feel true. This is why science communication is so challenging, and why it matters. The goal isn't just to convey information, it's to build intuition, to find analogies and comparisons that anchor the enormous to the familiar, to make you feel the scale, not just know it. When we say the sun contains 1.3 million Earths, that's an attempt to anchor the sun's size to something we know. When we say the photon takes 50,000 years to escape the core, we're trying to make the density and scale of the sun's interior feel real. When we compare a sunspot to the size of Earth, we're trying to make you understand what large means in this context. None of these comparisons are perfect. They're all approximations of understanding. The real thing remains beyond our intuitive grasp. but that's okay. That gap between what we can know intellectually and what we can feel intuitively is where wonder lives. When you stand outside on a clear night and look at the sun, through proper solar filters, of course, knowing what you now know, you're holding a contradiction. The star looks small, it looks manageable, it looks like something you could point at casually. But you know it's not. You know it's a roiling furnace of nuclear fire. You know its atmosphere is hotter than its surface, for reasons we're still unraveling. You know it erupts with storms larger than planets. You know its influence extends to the edge of the solar system, and that you live inside its weather. That combination, the small-looking disk and the vast, violent reality behind it, is one of the most powerful experiences science can give us. The universe is not what it appears. It is stranger and vaster and more violent and more beautiful than it looks from here. And knowing that, even if we can't truly feel it, changes how we see everything. One of the themes running through this entire documentary is interconnection. Nothing in the universe exists in isolation. Everything is connected to everything else through gravity, through electromagnetism, through the flow of matter and energy. The sun and Earth are connected, not just through gravity, which keeps Earth in orbit, but through the solar wind, which shapes Earth's magnetosphere, through solar radiation, which drives Earth's weather and powers Earth's biosphere, through the magnetic field that the sun carries into interplanetary space, which interacts with Earth's own field. The sun is connected to the other stars of the galaxy through the interstellar medium, the diffuse gas and dust between the stars. The sun moves through this medium at about 20 kilometers per second relative to the local standard of rest. The heliosphere, that bubble of solar wind we discussed, plows through the interstellar medium, creating a bow shock upstream and a tail downstream. The properties of the interstellar medium affect the heliosphere. If the sun passes through a dense molecular cloud, something that happens occasionally as the solar system orbits the galaxy over hundreds of millions of years, the heliosphere would be compressed. Galactic cosmic rays, which the heliosphere partially blocks, would penetrate more deeply into the solar system. Earth's cosmic ray exposure would increase. This might affect Earth's climate. The sun is also connected to its past. The heavy elements in the sun, carbon, oxygen, iron, all the elements heavier than helium, were made in previous generations of stars and scattered into the interstellar medium by supernova and stellar winds. The sun formed from this enriched material. It carries the chemical legacy of those ancient stars. And the sun will be connected to its future. When it eventually dies, shedding its outer layers in a planetary nebula, those layers will mix with the interstellar medium. They'll be enriched with the carbon and nitrogen and oxygen that the sun makes during its red giant phase. Those elements will be available for the next generation of stars and planets. The sun is not an isolated object. It's a node in a vast network of matter and energy, connected to its past and its future, to the local interstellar medium, and to the galaxy as a whole. We, living on Earth, are connected to all of it. We are made of atoms forged in previous stellar generations. We live on a planet shaped by 4.6 billion years of solar energy. We breathe oxygen produced by life that was powered by the sun. We eat food produced by photosynthesis. Our entire existence is downstream of stellar processes. We are not observers of the cosmos. We are participants in it. We are products of it. We are, in a very real sense, the universe reflecting on itself. That's worth sitting with. Throughout this documentary, we've moved between the technical and the emotional, between the scientific and the philosophical, between facts and feelings. That's deliberate. The best science communication doesn't just convey information, It tries to convey the experience of scientific discovery, the wonder that scientists feel when they look at data and see something unexpected, the excitement of solving a puzzle, the humility of realizing how much remains unknown. When the Parker Solar Probe flew through the Sun's corona for the first time, when its instruments confirmed that it had crossed the Alfvén surface, the scientists in the mission control room cheered. Not because the mission was over, but because it had just begun in earnest. Because a boundary had been crossed. Because we had, for the first time in history, touched a star. That moment deserved cheering. When Richard Carrington saw those two bright patches of light move across the sunspot group on September 1st, 1859, he ran to find a witness. He couldn't contain his excitement. He knew instinctively that he was seeing something significant, something no one had seen before. That instinct, that excitement, that's science too. When Hannes Alfvén proposed that the sun's corona could be heated by waves, and when other physicists dismissed his ideas, and when he persisted because the mathematics demanded it, and when he eventually won the Nobel Prize, that's science too. The long game, the willingness to be wrong, the commitment to following the evidence wherever it leads. The sun has inspired wonder in humans for as long as we've been human. The mythologies we discussed at the beginning of this documentary, Ra, Tonatiuh, Helios, Inti, Sol, Surya, Amaterasu, they're all attempts to grapple with the mystery of that light, to give it meaning, to understand our relationship to it. Modern science is a continuation of that impulse, more rigorous, more systematic, more powerful, but driven by the same fundamental curiosity. We look at the sun and we want to know what it is. We always have. We always will. The sky above us has never been empty. We have always been living inside a star's weather. And the wonder of that, the genuine, profound, lasting wonder of that, is something no amount of scientific understanding can diminish. If anything, it makes the wonder larger. Thank you for joining us on this journey, from the campfire analogy to the corona, from sunspots to CMEs, from the Carrington event to the Parker Solar Probe, from magnetic reconnection to the mystery of coronal heating. You now know more about the sun than most people on this planet. You understand what sunspots really are, why they're darker than their surroundings but still hotter than any furnace. You understand what a solar flare actually does, not just disrupt satellites, but how it disrupts them and why. You understand the terror and the scale of a coronal mass ejection. You understand that our civilization is vulnerable in ways most people never think about, and you understand the wonder of it all, that the sun is not boring, that it's not simple, that after centuries of study and decades of space exploration, it still keeps secrets from us. The corona heating problem remains unsolved. The exact mechanisms of CME formation are still being worked out. The prediction of solar cycle amplitude is still imprecise. There is so much left to discover. And that's exciting. Science is not a collection of finished answers. It's a process of inquiry that never ends. Every answer generates new questions. Every discovery reveals new mysteries. The universe is always deeper than our current understanding. The sun will keep us busy for centuries. Every morning, the sun rises. You see it through your window. You feel its warmth. You go about your day. You check your phone. Your GPS guides you. Satellites pass overhead. Electricity flows through the walls. Everything works. Everything is normal. But now you know. That quiet light is the surface of a storm. Those gentle rays, life-giving, warm, familiar, are the exhaust of a nuclear furnace that, converts 4 million tons of matter into pure energy every second. And the space between you and that star is not empty. It's filled with plasma, with magnetic fields twisting and coiling, with particles streaming outward at 1,000,000 miles per hour, with shock waves and turbulence, with Alfvén waves and magnetic reconnection events happening continuously. We live inside the sun's atmosphere, not metaphorically, not poetically, literally. The heliosphere, the bubble of solar wind surrounding our solar system, extends far beyond the orbit of Pluto, out past the Kuiper Belt, 100 times farther from the sun than Earth is. Every planet in our solar system exists within the sun's domain. The solar wind pushes against interstellar space, creating a boundary called the heliopause, the edge of the sun's influence. We are deep inside it. Earth exists in the weather of a star, and that star is not calm. It never has been. It churns, it twists, it erupts. Storms larger than planets tear across its surface and launch into space. Some of them miss us, some of them hit. We've been lucky so far. The worst storms in recorded history happened when our technology was simple enough to survive them. But luck runs out. One day, maybe in our lifetime, maybe in the next century, but certainly someday, another storm like the Carrington event will come. Maybe worse. We know from studying other sun-like stars that they produce superflares far larger than anything we've recorded. Our sun is capable of it too. And when it comes, we'll see the auroras again. Curtains of light dancing across the sky, far from the poles, visible from the tropics. Beautiful and terrifying at once. We'll watch satellites go dark. GPS will fail. Power grids will strain. Some will collapse. Communication networks will falter. And in that moment, we'll remember something important. We are not separate from the cosmos. We are part of it. We live on a small planet, orbiting a star, and that star is alive with activity. It breathes, it storms, and sometimes it reaches out and touches us. We are and have always been living inside a star's weather. But here's the other side of the story. We're not helpless. We're not passive victims of cosmic forces beyond our control. We're curious. We ask questions. We build instruments. We launch spacecraft into the fire to measure and understand. We take the star that gave us life and we study it. We try to unravel its mysteries. We work to predict its behavior. We're building a picture piece by piece, dataset by dataset. The Parker Solar Probe is out there right now, closer to the sun than any human-made object has ever been, surviving temperatures that should destroy it, measuring the corona from the inside, sending back answers. The solar orbiter is studying the sun from different angles, capturing the first high-resolution images of the solar poles. Ground-based observatories like the Daniel K. Inouye Solar Telescope in Hawaii are watching the sun every day with unprecedented detail. And maybe one day we'll truly understand. We'll know why the corona is so hot. We'll know exactly how CMEs form. We'll be able to predict space weather days or even weeks in advance. We'll learn to live safely with our star's weather. But even if we solve every mystery, even if we understand every mechanism, the wonder won't fade. Because the sun is not just a physics problem, it's the reason we exist. Every atom in your body was forged in the heart of a star. Not this star. The sun is too young, only 4.6 billion years old. But ancient, massive stars that lived fast and died violently billions of years before our solar system formed. Those stars fused hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, all the way up the periodic table: silicon, sulfur, iron. They built the elements of life. And when they ran out of fuel, when iron began to accumulate in their cores and fusion could no longer produce energy, they collapsed and then exploded. Supernovae. Some of the most violent events in the universe, briefly outshining entire galaxies. Those explosions scattered the elements they'd created: carbon, nitrogen, oxygen, iron, everything into space. Into vast clouds of gas and dust that drifted through the galaxy. And those clouds collapsed. Gravity pulled them together. New stars formed. New planets condensed from the disk of material swirling around those new stars. One of those planets was Earth, and one of those stars was the Sun. We are made of stardust. Every atom of carbon in your DNA, every atom of calcium in your bones, every atom of iron in your blood, they were forged in stars that died before our solar system was born. We are made of stardust, held together by starlight, living on a world that orbits a star. The sky above us has never been empty. We have always been living inside a star's weather. We've just been too distracted to notice, too comfortable, too focused on the ground beneath our feet to look up and understand what that light really is. But now you know. And maybe the next time you see the sun rise, the next time you step outside and feel its warmth on your skin, you'll pause. You'll think about the storms raging across its surface, the magnetic fields twisting beneath, the granulation cells boiling, each one the size of a country, rising and falling in an endless cycle. The photons that took 50,000 years to escape the core and 8 minutes to cross space. You'll think about the fact that the sun is not calm, that it's a star, alive with energy, constantly in motion, constantly erupting, constantly reaching into the solar system with its weather and its light and its storms. And you'll feel small, but also connected, because we are not separate from the sun. We are its children, born from its light, shaped by its gravity, warmed by its energy, protected, barely, by the thinnest of shields, by a magnetic field and a thin layer of air. And every day we wake up to a miracle. The storm continues, the sun churns, the magnetic fields twist and snap, flares erupt, CMS launch into space, the solar wind blows, the aurora dances at the poles, the photosphere boils, and we survive. We more than survive. We thrive. We build. We explore. We ask questions. We send spacecraft into the fire to understand it better. And maybe that's the real meaning. Not that we're vulnerable, not that we're at the mercy of forces beyond our control, but that we're alive, conscious, curious. We're a part of the universe that has learned to ask questions about itself. We're stardust that has learned to study stars. And that might be the most extraordinary thing in the cosmos. Thank you for being here tonight. Thank you for taking the time to look up, to wonder, to ask what that light really is. This is Infinite Science. We'll see you in the next one. Stay curious. Keep looking up. And remember, the universe is stranger and more wonderful than we imagine. It's stranger than we can imagine. But we're trying anyway, and that might be the most beautiful thing of all.